We're going to look at some structures today that are going to let us predict molecular polarity based on the overall bond polarity and the shape of the molecule. And the first one we're going to look at together would be CH3Cl. Carbon has 4 valence electrons, each hydrogen has 1, and the chlorine has 7. So that'll give us a total of 14 valence electrons to play with. We've got our C in the middle. Each hydrogen is going to attach on, and of course our chlorine as well. And then our 6 electrons that we still have to play with are all going to go to chlorine since hydrogen really doesn't want any more. If we checked our formal charges to see how this one looks, carbon starts with 4 valence electrons. It also has 4 bonds. 4 minus 4 would give a 0 formal charge. Hydrogen has 1 valence electron and 1 bond, again, 0 formal charge. And chlorine starts with 7, 7, 6, 5, 4, 3, 2, 1, 0, also a 0 formal charge. So this is really our best Lewis structure we can make. Honestly, without giving carbon an expanded octet, it's probably the only Lewis structure we can make. And since carbon is in the first period there, the second period, the first full row, first P room, it's not able to make an expanded octet because it doesn't have any D electrons to work with anyway. So we have our good Lewis structure. We check our bond polarity, and in order to figure out our bond polarity, we subtract our electronegativity to find the difference. And we realize that we have an electronegativity difference of 0.45, which are polar bonds, and that would be between the carbon and the hydrogen. Carbon is more electronegative than hydrogen, so those bonds would look like this. And then we would also check the carbon-chlorine electronegativity difference. That's a 0.61 difference, also a polar bond, this time pointing toward the chlorine. At this point, it's going to be really tempting to try to make a call on the molecular polarity, but before we do that, we really should look at the VSEPR theory and figure out what the shape of this molecule really looks like. Our electron domain geometry here, AB4, no lone pairs on the center atom, AB4 would be tetrahedral. And since all of those spots are bonded atoms, none of them are lone pairs, this is both the electron domain geometry and the molecular geometry. So if you remember back to your Chem 1 days, tetrahedral shapes are drawn so that these two, along with this guy here, are on the same plane. This atom is coming out of the paper at you, and then this one is going back behind. It really looks like this guy. And please don't judge me for having random molecular model kits at my house. I'm going to color one of these in just so we remember that one of them is different than the other 3 bonded atoms. This would be our chlorine, these would be our hydrogens. So these dipoles would be pointing in toward the center atom. This one is pointing away from the center atom, which means overall the electrons kind of be pushing up toward the top of this guy. If we think about it in terms of a positive plate here and a negative plate here, if we put this molecule within the electric field, it would want to rotate itself so that the negative end is close to the positive side and the more positive end is close to the negative side. And because we would have that shift, this would be a polar molecule. Hopefully that makes sense. The next example I want to talk to you about is actually going to wind up with an expanded octet. We're going to look at BrF3. Now this is full of halogens here. 7 times 4, we would have a total of 28 valence electrons to work with, which means even though we only have 3 atoms bonded to our center atom, that's only going to give us a total of 24, 25, 26, 27, 28. So now we have 1, 2, 3, 4, 5 things around our center atom, which means if we're just looking at the electron domains, that's actually based off of trigonal bipyramidal, or trigonal bipyramidal if you prefer. If you remember, that's the one that looked like a linear that has a trigonal planar kind of going right through his center. So these three we call equatorial position, and these two, those are called the axial positions. And here we have a time when these are actually different angles. We have a 120-degree angle between the equatorial positions. We have a 90-degree angle between the equatorial and the axial. And then these two axials are obviously 180 degrees apart. And the reason that I'm going to bring your attention to that is because there's actually a right and wrong way to take the atoms away when we're looking at putting lone pairs in to replace them. So we're starting with something that looks like this. And we could absolutely take away these two and wind up with a shape that looks like trigonal planar. We could also take away two of these and wind up with something that looks like a T shape, or you could try taking away one of each and getting this really weird, almost like a trigonal pyramid, but the angles are off. These things would be called isomers because you've got the same type of atoms bonded, you have the same type of single bonds, but they're in different positions. And one isomer and one shape is definitely better than the others. So really what I need you to remember is that these equatorial atoms, they only have two neighbors that are 90 degrees from them. The other neighbors would be 120. The axial positions have three neighbors that are 90 degrees from those, and again, 180 across. The electrons that we wind up putting in first are the ones that are around the equator. These are the ones that the atoms get replaced with those lone pairs first. So if you remember back, if you replace one, you wind up with a seesaw shape. Seesaw. It's also called a distorted tetrahedron, but that's just crazy. And when you take away the second one, like we have here, that is our T shape, and that is the best isomer. It's the one that's the most stable. So we have our T shape. We check our polarity. That's 3.98 minus 2.96, a difference of 1.02. Another polar bond pointing toward fluorine, which means if we look over here at our actual shape, this one's going left, right. This one's going down. Nothing's going back up, which means overall, we've got a dipole moment that's going to be pointing down toward this atom, which means this side winds up being a little bit positive, this side winds up being a little bit negative. So if we bring him over here, the negative side would align itself toward the positive side would align itself toward the negative. This is also a polar molecule. And while we're looking at BRs and Fs, there's one more that I want to kind of walk you through quickly. This time, instead of BRF3, let's expand that octet even a little more, and let's get BRF5. So now we're working with a total of 42 valence electrons. 42 valence electrons means it's a lot of dots. So far we're up to 40, so we're going to go 41, 42. We have 1, 2, 3, 4, 5, 6 electron domains, so that electron domain geometry would be octahedral. this is the shape we're building it off of, but we're replacing one of these guys with the lone pair. So we're taking one of these atoms off, and now we're left with this shape here. And if you remember, this one would be square pyramidal or square pyramidal, so that would be our molecular geometry. Square, because it has a square bottom, pyramidal, because it also has that point to make a little pyramid on top. When we're drawing these, we usually can do something like this to show a couple of them coming out of the page and a couple of them going into the page. And as we're looking at this, you're going to notice that these four are directly across from each other. So really, when we're thinking about this 1.02 difference, we're still having these dipoles on our bonds. These four would all cancel out though. However, this one doesn't have anything to cancel it out. It's not a symmetrical shape because we did replace some of those electron pairs, which means if we put him over here, we wind up having this side being a little bit negative again. The other side would be a little bit positive. They're also going to line up like that. Also a polar molecule. So then just one more thing before I turn off this video. Just a brief reminder about angles here. We know that this tetrahedron, because it doesn't have any lone pairs of electrons, its angles would be exactly what we would expect them to be. That would be the tetrahedral angle. Here and here, even though when we're building them with these kits and when you build them online using that website for the Vesper shapes, it looks like perfect angles here. Keep in mind this one is going to be pushing all of these guys away just a little bit more than expected. So these are going to get bent down a little bit more. It's not going to be a perfect flat shape there. And same here, these guys will be pushing away more than these guys are. So things just get a little bit distorted, and that's where you wind up with all those angles that will say things like less than 120 or less than 109.5. The less than angles are just showing that the electron pairs are repelling more than the bonding pairs. That's all. Hopefully that helps.